Okay, I do have all of the tests graded, and I hand graded all of them that missed 2 out of the final 3 questions. The high score was a nice 98.33, and the second score was 91.33. But then the third score was 79.67. So there was a really big gap between the top 2 and the rest. So I'm going to be trying to look at the scores a little bit more. There are still 2 people who haven't taken the test, even though I'm going to give them a different test. I'm not going to distribute the test or anything until after it's done. So I will upload scores today so you can see the scores, but I won't distribute the material until we have the last 2 taken. How did the test feel?
I would do the work, and then my answer would be one of the options. That was reassuring.
Unfortunately, I actually try to calculate errors for the answers. Like, when it's supposed to be A times B, I also do A divided by B and B divided by A.
Yeah.
It's not the correct answer in random numbers.
Yeah.
But yeah, it is.
That's why I said reassuring.
Yeah.
I didn't say it made me 100%.
One of the things I noticed in my hand grading was that there were people who had answers circled on their test form than they put on the Scanton sheet. And that makes it a little tough to figure out how I'm supposed to grade it if you have 2 different answers. There's one person that score would have been different significantly, like by 6 or 7%. The Scantron ones were right, the ones in the test were wrong. So I went with the Scantron ones. But do try to, be a little careful on that, to make sure you answer what you intended to answer. Hopefully, we're all ready to move on to magnetism. We've already started some of it. In fact, with the reading quizzes, you're now a full lecture ahead of where I am with the reading quizzes, which is a little shameful, but we will survive. You guys feel like you're learning a lot about magnetism from the reading quizzes? I give you some answers this evening. How much time do you spend on reading quizzes? Too much?
Yeah.
Depends on if you want to do well or not. Yeah, I can answer really quick if I didn't want the right answers. I mean, the goal is not for it to be time consuming. And I know some of the questions are ambiguous or don't seem to make sense. I kind of am considering going back to just doing my own handwritten reading quiz questions because mine were a lot more straightforward.
Yeah. Like I read the section and I'm doing it, I go back to the section, I can't find it anywhere. Sometimes it's in the wrong section or a section ahead or 2.
Mm-hmm.
I know one time I sent them a full message hey, you need to make these things clear.
Did they respond?
No.
They could come out of their class.
I have sent corrections to them a number of times, and 6 months later, I'll get a reply. That problem's been changed. I hope so. Anyway, yeah, their turnaround time is not very good. Okay, so enough complaining. We're going to talk about magnetic force on charts. We ended last lecture period with one slide, this one, where we were talking about the situation where you can get a net force of 0 on a moving charge in electric field and magnetic fields. And the last thing we did with this was determine the direction the magnetic field would have to be to get a net force of 0. So we used the right-hand rule to verify that the directions shown in this picture are correct. Now, the important thing here is if you have just the right directions and magnitudes for the electric and magnetic fields and the speed, all 3 of those things have to be just right, then you can have a net force of 0. So in that case, you have to have this vector equation, QE, the charge that's moving, multiplied by the electric field it's moving through, plus QV cross B is equal to 0. And all of a sudden you realize, wait a minute, the charge doesn't even matter, does it? As long as E is equal to V cross minus V cross B, then it will travel with zero net force due to the electric field and magnetic fields. Now, we're actually going to come back and see this relationship at a later time, but right now we're going to look at how these things can be used to our benefit. So first here we have a mass spectrometer. Anyone used a mass spectrometer, chemistry class? Wes? Okay, a lot of you have. So there are different types of mass spectrometers. There are quadrupole mass spectrometers where you make, magnets have two poles, north and south. You make a quadrupole magnetic field, a magnetic field with four poles, that's going to be two north and two south, not some bizarre thing. And you put varying magnetic strengths on those, and it's pretty complicated. But then you have the simple one. This is what I think is typically used in what they call an RGB or RGA, residual gas analyzer, which is most likely what you're going to use if it's a low-level mass spectrometer. And so you have charged particles. Need to be charged particles because we're going to use electric force and magnetic force. Electric field doesn't affect things without electric charge. Magnetic field doesn't affect things without a magnetic charge or that have a moving electric charge. So in order for this to work, we need to have charged particles, hence the ion source. And then you notice here we have electric fields are the green lines. So let's say that I had a positive charge here. If I have a positive charge of +1, that means it has one missing electron, singly ionized. What direction is the force due to the electric field going to be on that charge? That is right, Wes. Anyone else? That's right, Madison. Okay. Not a lot of people answering, but at least 2 out of 2. I'll assume that everyone else is just, too sure that they're right. So we would have a force due to the electric field that's in the same direction as the electric field. Because of this equation. And so the magnetic field is put at a perpendicular direction to both the velocity and the electric field, such that it's going to make a force that's the opposite direction. And so, once again, if you look at the magnetic field, you can verify that if V is going that direction and B is into the screen, then the magnetic force is going to be up. And so we have a magnetic force that's up, that is what's the point of this? If we have a net force of 0, it's just going straight, right? Seems like there's no point. Here's the point of it. What happens to those forces if you speed up the particle's motion? If it's going too fast, what's going to happen?
The influence of the forces pulling up and down is going to be less.
Which one? He's correct. One of the forces is going to change when you speed up. Which one's going to change? The magnetic force. You speed up, that magnetic force is going to get bigger. And so then you'll have a net upward force, and it goes up, doesn't go straight. If it's slow, then you'll have a downward force. It doesn't go straight. So this is what we call a velocity selector. You set the strengths of the electric field and the magnetic field so that QE equals QVB. Notice I dropped all vector signs and the cross product. The reason is we're now just saying the magnitude of one force has to be the same as the magnitude of the other. Because they're perpendicular, QV cross B has a magnitude of QV times B. Remember, cross product is AB sine of the angle between the two. So if theta is 90 degrees, which it is here, then it's just A times B is the magnitude. So that's why it's just VB there. So that means that I can cancel my Q, and then the velocity that's going to go straight is going to be the electric field strength divided by the magnetic field strength. So I select the speed of my particles by the ratio of the electric field to magnetic field. Why is that important? You might be, I don't care how fast the particle is going. Well, when the particle enters the magnetic field, then something really interesting happens. So this here is a different magnetic field. This is the actual spectrometer, mass spectrometer part. So you have the beam comes in as a narrow beam, but if I have a particle traveling in the presence of a magnetic field, so let's once again, just to make life easy, say this is plus Q. What direction is the force on that particle? You go. Right hand, orient so my index finger is pointing the direction of V. Change it so my middle finger points the direction of B. My thumb points up. So I have a force that's going up. So black. That force is perpendicular to the velocity, so what's it going to do? If it's perpendicular to the velocity, it cannot make it go faster or slower. What can it do? It's going to change the direction that it's traveling. So it's going to deviate in the direction of the force. So a split second later, the particle is going to be going like this. But now what direction is the force?
It's kind of going diagonally back a bit.
It's like that, right? And as it keeps going, the force keeps changing direction, so it's always perpendicular. And so it goes in a circle. So a particle moving perpendicular to a magnetic field will go in a circle. While things go in a circle, we have a way to deal with this. We know Newton's second law says sum of the forces is equal to mass times acceleration. So if it's going to go in a circle, we say sum of the forces toward the center in the centripetal direction is equal to mass times the acceleration toward the center. But if something's going in a circle, we know that AC has to be v squared over r, the speed squared over the radius of the circle. So looking at this, what is the force toward the center of the circle here? It's FB. It's the magnetic force. So I have the magnetic force is equal to mv squared over r. But since the magnetic force is QVB, then I have now I need to be clear, I have two magnetic fields in this problem. So I'm going to call this B2, just so we're clear which magnetic field it is. So this is B2 here, and this one here was B1. So the speed is electric field over B1. So QVB2 is equal to mv squared over r. What are we looking for here? If it's a mass spectrometer, what are we trying to solve for? By the definition of a mass spectrometer. Mass, right. We want to be able to differentiate them by mass. So I solve this for mass by dividing both sides by by v squared. And multiplying both sides by r. And so I have mass equals QB over V R. And that was B2. Now using the fact that V was equal to, E, the electric field over B1, so the mass will be equal to the charge of my ion times the product of those two magnetic fields divided by the electric field, all times the radius. So if I measure the radius and I know what the two magnetic field strengths are on the electric field is, and the charge state, I get the mass. Now, this brings up a weakness with the mass spectrometer. Because I started by saying, let's assume that we have a particle with a charge of +1. How do I know I don't have the particle with a charge of +2? I mean, unless it's helium, I don't. And so you have to realize when you're using mass specs, sometimes you'll have a Q that's 2 when you think it's 1, and so you'll have a line that you think is 1 mass when it's actually like twice that? No, half that. Anyway, that's a problem you have to be aware of. So when I was in graduate school, I did a lot of mass spectrometry, and that was the kind of thing I had to look at. I had a quadrupole mass spectrometer, which gives you really good detail, and you can actually see the difference in 2 different molecules that both have a nominal mass of 28 atomic mass units, because they're not exactly 28, and you can see the difference in them. And so you have to be aware and look for that. This is what this one, if it's doubled, would be to break it apart. I don't know, did you guys have to do that with your chemistry stuff or no? So that's the basis of how a simple RGA, residual gas analyzer, does its mass spectrometry. It uses the force on a charge due to electric field and magnetic field. Any questions about that? It's a very useful thing. Is that a question, Gene? Or Eugene, not Gene.
No, I was just wondering where you got the velocity for that side.
Okay. Here is an example that is similar how we make our the old style television with cathode ray tube. I already talked about it before, having the things that go up and down and things go left and right using electric fields to control where the beam hits. But there's another thing there, the velocity selector, because we like to have color televisions. Any idea how a cathode ray tube television works?
They're like sense scans.
Okay. You shoot electrons at the screen. It's called a cathode ray tube because the electrons are being shot off of a cathode, as you see there at the left side of the picture. And so it was first discovered that there was some kind of beam that would come off of the cathode. And then with studying it, by putting in electric fields and magnetic fields, it was quickly determined, hey, this thing has to be an electrically charged thing, and they could determine properties by doing experiments like what we're doing here. But then what makes light? When the electron hits the screen, what makes light?
Excitation?
It's excitation. You have phosphors, which is not something with phosphorus, but it's chemical compounds that when they absorb the energy of the electron, you'll have electron energy levels in the molecule go up to a high level, and then they fall down a specific amount and give off a specific color. You have to have the right energy electron to excite them. And so you can make a phosphor that this one responds to a 1,000 electron volt electron. This one responds to a 2,000 electron volt electron. So you can hit the same patch that has 3 different kinds of phosphors, and depending on the electron's energy, it'll only excite one of the 3 phosphors. But that means you have to carefully control the energy of the electron beam. And so that's why there is a velocity selector stage in the cathode ray tube. So you can have, this is shooting this energy electron, this is shooting this energy electron, this is shooting this energy electron. And then you're actually scanning 3 beams. So that's another practical example, not as common as it was 20 years ago. This here is actually talking about the work of Thomson, notice there's no P in his name, that established that you have negative particles coming out of that cathode because he was studying what happens in electric field and magnetic field. Now, some more simple applications of this. There's a blood flow method. Now, when I look at this, I'm like, do they cut people down to do this? Or, how are you going to measure the voltage difference across one side of a vein or artery if you don't cut down to get to it? So I don't know exactly how this may or may not be used in hospitals, but you can measure the blood flow, like arterial blood flow, by putting a magnetic field across an artery or vein, as the case may be, and then measuring the voltage that's produced. Because if I have charged particles in the blood and I put a magnetic field, there's going to be forces to make a positive charge go to the top and a negative charge go to the bottom. So that means I'm going to start loading up the top with positives, the bottom with negatives. And that's going to be just like a capacitor plate. Capacitor plate, you have the positive, you have the negative. Between them, you're going to have an electric field that, if it's a uniform electric field, would be electric field is the voltage difference divided by the separation. So you have your electrodes here, you know what the separation is, and you measure the voltage. You can determine the electric field, and the voltage is going to increase until the net force of the charged particles is zero, to where the force QVB caused by a magnetic field is equal to the force QE caused by the electric field. And so just like our velocity selector, this is going to charge up until you reach a voltage here that tells you what the speed of the charge carriers in the blood is. It's a really cool idea, right? It's much better than cutting an artery and measuring how much blood comes out per second. The Hall effect is basically that idea. The Hall effect is actually, in my experience, it's used to measure the strength of a magnetic field. For the Hall effect, you take a probe, and the probe is something relatively thin, made out of like a semiconducting material, and then you make current flow through it. So you have a controlled amount of current going through it. So obviously you have to have a wire to bring the current back. But that current's going through this probe. And then you measure the voltage difference from one side to the other. Just like with that blood flow meter, what you have is, if we look at the long side now, we have charge carriers that are going like this, and you have a magnetic field like this. And so that's going to make, if it's a doesn't matter if it's a positive charge or a negative charge. The charge is going this direction, the magnetic field's that way, it's going to make an upward force on the charge. And so once again, just like the picture with the artery, you're going to have the charge come up to here. Now notice I'm putting Q, 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 Q. Not because it's crying, but because that's where the charge is going to go. Now, if I had a current going the other direction, I should have made those red. I'm going to make them all red. If I had current going the other direction, it would go the opposite, but the charge goes to the top. But here's the cool thing then. It doesn't matter if it's positive charge or negative charge. The charge is going to go to the top, and then it's going to make an electric field because I'm going to be missing charge in the bottom to counter the charge at the top. So I'm going to have an electric field in there, and I measure the voltage difference across here, and by knowing this distance, I can calculate the electric field, and it's going to reach a balance when QVB is equal to QE. Then I could, in theory here, determine the speed. But that's not actually what I want to do. I mean, it's what some people want to do. It's not what I want to do. What I want to do is to determine which type of charge it is. I can determine which type of charge it is because if it's a positive charge, the top will be positive, right? If the thing carrying the current is positive charge, it'll be positive charge at the top. If it's negative, it'll be negative at the top. And so one of the cool things you get out of this Hall probe is it tells you what kind of charge is moving in your material. So in a typical metal, what type of charge is moving? Electrons. So if this was made out of metal, I would have electrons there at the top, and the bottom would be positive. If we make it out of semiconductors, some semiconductors will be positive on the top, and others will be negative on the top. So the semiconductors somehow have a positive charge flow. And then we get all kinds of concern, like what's moving? It's not protons. We can be sure of that. And so the answer we come up with is it's holes. It's missing electrons that are migrating. So you have this missing electron that's going this way. What's really happening is the electron goes from here to here, and now the missing one is here. The electron goes from here to here, and now the missing one's there. But that behaves as if it's a positive charge carrier. And so in those semiconductors, we can say the charge carrier is positive, the current's flowing in the same direction as the charge carrier is moving. But coming back to this, what is this fundamentally used for? It's fundamentally used to determine the magnetic field. So you put the current in, and we're going to switch to the equation for force on a current, and knowing what the current is and measuring the electric field allows you to know what the magnetic field is. So we need to move further in this before we can get to how we get that from it. This discussion here is about how you find the drift velocity, how fast the electrons are going, because, whoops, it was here, because you have this V variable. So the way we have it, you can use it to find the speed of the electrons. Let's shift to the force on a current. So we had force on a charge was QVB. If I have a current flowing, it's a whole bunch of Qs. And so we can go through. You don't have to memorize this. I am not going to ask you any questions about this, okay? Not going to have any questions about it. But what this is doing is showing the procedure to go from the force equation we learned to force equals IL cross B. Now there's a weirdness about this equation. Current has a direction, right? We learned, like in the test yesterday, you had to draw the arrows, draw which side is positive, negative, given the direction of the current flow. So current has a direction. And yet if you look at that equation, current is a scalar. And any reasonable person says, why doesn't current have the vector sign? And the reason is kind of convoluted. In theory, current is not a vector. It can't be a vector, it's a scalar. It's because it's done with an integral of the current density vector. And so we introduced the L vector, which is the length of the wire in the direction the current's going. In the direction the current's going is how we get the direction for that L vector, because the I technically can't be a vector. So for all intents and purposes, I always think of it like this. Because I know I has a direction, I'm going to point my index finger in the direction of I. Because if you have the L vector, you point your finger in the direction the I is flowing to get your direction for L. But this is the technically correct equation. Force equals IL cross B. So if you need to go, you can go, Madison. Here. Not holding you hostage here. Good luck making your flight. So what's important here? If I have a current carrying wire and it's in a magnetic field, there's going to be a force acting on it. And that force is going to be perpendicular to the current and perpendicular to the magnetic field. And so we're going to have lots of problems involving this. Yeah, guess what you're going to be doing now, sometime between now and Monday night. Problems like this. So steps to solving a problem with the force on a current carrying wire. Number one is to look and make sure that the force isn't zero. Checking the zero conditions is really easy. So the magnetic force is 0 if the current is 0, or if the wire is parallel to the magnetic field, because remember, IL cross B is multiplying the perpendicular parts. So if the current is going parallel to the magnetic field, there's not going to be a force. Or then you have if the magnetic field is 0. So you want to check those 3 cases first, just to make sure, get the easy zeros out of the way. Once you've established, okay, nope, it's not a 0 magnetic force, then you need to determine the angle between the direction the current is flowing and the magnetic field. And notice how it says L vector, and I just said the direction the current is flowing. And then you just use the magnitude of the force is ILB sine theta, and the right-hand rule to find the direction. So let's go straight to applying this. Oh, yeah. This is actually a problem with the Hall effect. Let's do it. Let's do it. A flat slab of semiconductor has a thickness T that's 0.50 millimeters. So that is thickness going left to right. And a width W that's 1.0 centimeters, that's top to bottom. Or the width was into out, I guess. And a length L is 30 centimeters. A current of 2 amps flows along its length to the right. So the current is flowing. You can see the magnetic field of B, 0.25 Tesla, is directed into the page perpendicular to the flat surface. Assume that the carriers are electrons. Okay, that's not important to me. What is the magnitude of the Hall voltage across the slab? That is a good calculation. So let's start with simple questions. A, Roman numeral 1. Why is there a Hall voltage to begin with? Why is there going to be a voltage measured by that voltmeter? An electric field is going to be created because of the magnetic field acting on the charges. So in this case, I will start with what's the force on a charge? Force due to magnetic field is IL cross B. So that's equal to the current times the length times the magnetic field times sine of the angle between the two. Well, the length is horizontal. The magnetic field is into my page, so the angle between them is 90. So sine of 90 is just 1. Arrow to 1 on that. So the force is ILB. I can put in numbers, but why would I? What direction is that force going to be? This one here I want us to actually do. Whipping out our right hands as always. We have force is equal to IL cross B is our equation. What should our index finger point? What direction should our index finger point?
Left to right.
Why?
Because that's the direction of the velocity.
Not velocity in this case. Current. Because that's the direction of the current. Because it's electrons, the velocity is actually this direction. But the direction of the current is that direction, so we're putting an index finger in the direction of the current. And then what direction should my middle finger point? Into the screen because?
The direction of the magnetic field.
Right. And then my thumb points the direction of the answer. My thumb points up, so there's going to be an upward force on the charge carriers. So the charge carriers go up here. It says the carriers are electrons. So I'm going to have electrons on the top, which means I'll have missing electrons or positive charge on the bottom. Question?
So how do you know that the magnetic field was into the screen and not out of the
Because I have these X's. The X's are supposed to be the fletchings of the arrow, so it's going away from you.
Oh, yeah. Proud about that.
All right, so we have the direction of the force and we have the strength of the force. So we're going to have charge accumulate on the top and the voltage increase until what's going to make the voltage stabilize? Why don't we keep building charge infinitely on the top?
Or will the electric field.
Electric field. If I have my positive charge on the bottom and negative on the top, then that makes an electric field like this. Right? And so with that electric field, that's going to put a force on the charge carriers. So now these electrons are going to have a force that's force electric is equal to QE. Well, the electric field is up. So what direction is the force due to electric field? Down, because they're electrons, they have a negative charge. So it's in the minus up direction because Q is negative. And so we're going to have a downward force due to the electric field. So this force here is directed up. And then I have the force electric. So there's my direction up, is equal to QE down. And we'll reach equilibrium when the two are equal to each other. So equilibrium when force magnetic plus force electric equals 0. So ILB equals QE. I know I moved it across the equal sign. One was up, one was down. So ILB up plus QE down. Move the QE to the other side. Yeah, that'd be ILB up equals QE up when I change the sign. And I drop the direction. So that's the condition that's going to be balanced, equilibrium. But we're not measuring electric field, we're measuring voltage. So then I have to use one last equation, that for a uniform electric field, V equals ED. Before the exam, somebody was asking me about this equation, it was on the equation sheet. On the equation sheet, it has I think it's delta V is equal to E dot D minus E dot D, I think it is. That's the technically correct form. In our case here, all I really care is I already have determined which side is going to be positive and negative. I just need the magnitude here. So my E is equal to V over D. And so that means my Hall voltage is going to be ILB times D over Q. And so I can measure that Hall voltage V, and since I'm controlling the current, I know what the charge carrier is, I'm controlling the magnetic field, the length and the D are already built in. By the way, that D now is going to be this distance, so it'd be W using the variables given. That's the Hall voltage. And the key here is things I control. Whoops. ILW over Q. And the thing I don't control is B. So I measure that Hall voltage and I can determine what the magnetic field is. That's how Hall probe, in my experience, is fundamentally used. It's kind of a cool problem, right? There were a lot of different physics ideas that we had to put together here. I've got to tell you, when I was your age, I got really confused doing this problem. Right? It's not like it was, oh, that was straightforward. That was simple. Everyone should get that. No, it was a little more complicated. But it helps us to put the ideas together of seeing how the electric force works, how the magnetic force works, and how we can come up with a novel and cool usage of it. More problems. This is actually the problem I thought I was going to do first. A 125 meter long power line is horizontal. So this is the power line up here at the top, and carries a current of 2,500 amperes toward the south. So you got north-south indicated. The Earth's magnetic field at this location is 0.052 milliteslas pointing north and inclined 62 degrees below the horizontal. So it's pointing north and down. So I can break it into components if I need to. What's the magnetic force on the power line? Assume that it's perfectly horizontal. How do we go about this?
Wait, the current south and the magnetic field is going north. Wouldn't they be parallel?
If the magnetic field really was north, yes. But it's north and inclined downward. Let's start with, because we're looking for the magnetic force, what's the equation for magnetic force? Okay, we had that first, but today we have the one that has length and current instead of QV.
So it's the cross product of the current length and the magnetic force.
Okay, so there's the equation. Now, the instruction said first determine if it's zero. So DJ had already considered that. Because it said north, he said, well, north and south are opposites, so that would be no force. But it's not straight north. It's 62 degrees down of north. And so that means it's not parallel, hence that one's not zero. The magnetic field's not zero. The current's not zero. Hence we have a force. So now I'm going to take this equation and break it into two pieces. Direction and magnitude. Magnitude. Okay. Does somebody want to lead us in applying the right-hand rule to this specific case? Okay, point your index finger and tell me which one you're pointing it with. Parallel to what?
I.
I. So he points his index finger that way because that's the direction of I. Then what do you do?
And then you point your middle finger down.
Down and at the angle shown, right? So it should be down and tipped back. What direction is the force?
It's going out.
It's coming out toward us, which one would expect that means that it's pointing east. Okay, so we've got the direction specified. That's one half of the problem. That was the easy half, by the way. The hard half is not hard. ILB. We're given I. By the way, 2,500 amperes. That's no joke right there. Then the length, we're given the length is 125 meters. The magnetic field is 5.2 times 10 to the minus fifth Teslas, right? Because it's milli, that's going to be minus 3. Move it over 2 more, minus 5. And then we have to have sine of the angle. So what is theta supposed to be?
It'll be in between I and B.
Between I and B. So I is this way, B is this way, so that's theta.
So it'll be 180 minus 62.
Okay, 180 minus 62. Now, here's a shortcut as long as you keep things square in your head. Sine is symmetrical about 90 degrees, right? And so sine of 180 minus 62 is the same as sine of 62. You can take either of these angles and you'll get the same answer. As long as it's between either side of the current and either side of the magnetic field, you'll be fine. So we could do sine of, let's see, that would be technically 118. Or we could do sine of 62. I choose 62 because I don't have to do any math in my head for that. Even though 180 minus 62 shouldn't be that hard. I could have messed that up. Probably did. So we just put that into the old calculator, and we get the strength of the force. How strong is that force? Did anybody calculate it? Yeah. What'd you get?
14.35.
Okay, we only have two significant digits, so to correct significant digits, 14 newtons. 14 newtons is not a very big force, but it looks like it should have been huge. What was the factor that made it so it wasn't a very big force? The Earth's magnetic field is pretty weak. In fact, you realize you're getting that kind of force out of the Earth's magnetic field, and you're kind of a little impressed then. And so that wire is going to be pulled a little bit to the east because of the current flowing through it. Good to know, right? Why do I have this slide a second time? Only God knows. Why do I have this slide a second time? Obviously, I made a mistake in putting my presentation together. Electric motors. We've got 4 minutes for electric motors. Electric motors can't be discussed in 4 minutes. An electric motor is something that you put electricity into it. So you're putting energy in, and it converts that electricity into mechanical energy. So it rotates because of the energy you put in. So it's something that's going to convert electric energy into kinetic energy. That's the purpose of an electric motor. And these days, they're becoming more and more important to us as we have cars that use electric motors. That electric motor in the car gives it a whole lot of torque, right? Right, Nate? Right. So you can have some electric vehicle will take a supercar off the line pretty much every time because they have so much torque in that electric motor. It may not take them in the long race, but they'll take them offline. Right, Nate? The reason I know these things is because he shows me videos of them. So how an electric motor works is something that is really important to us. In fact, we're going to learn about electric motors, and then we're going to move to electric generators. Electric generators are the opposite of electric motors. We actually looked at something like this before. We had heat engines and heat pumps. A heat engine was something that you put heat into, and it gave you mechanical energy. Whereas the electric motor, you put in electrical energy, you get mechanical energy. So heat engine, motor, same idea. A steam engine can be used to drive a vehicle, or an electric motor can be used to drive a vehicle. A heat pump was something that moved heat when I put energy into it. I put mechanical energy in and moved heat. A generator, I put mechanical energy in and I move charge. So the generator is like the heat pump. So we have a good analogy here. And I'm just not gonna lecture on this now because you're not gonna remember anything about the nitty-gritty details if I start now. But I can ask this one question before we go. What direction is the net force on this loop? Now, if you look at the loop, you have current flowing like this, like this, like this, and like that. Let's look at the force on each side before we answer. So if I look at side 1, is there a force on side 1?
No.
No is correct answer. Why is there no force on side 1?
Because it's parallel.
Because it's parallel, which I believe is what this meant. Either that or he was cutting. Or saying, stop. Is there force on this side?
Yes.
Yes, clearly there is because it shows a force arrow. How did they determine the direction?
With the magnetic force and the current in the right.
Right-hand rule. Index finger went the direction of the current. Middle finger pointed the direction of the magnetic field. And thumb points into the page so that this is down into the page. Directions is hard. On side 3, once again, you have the parallel case, so no force. Side 4, you have the current going the opposite direction of side 2. Same magnetic field, so opposite direction, up. So do we have a net force here
Which one?
on the entire loop?
Yeah.
Net force is 0 because you have as much up and as down. Does that mean the motor doesn't turn? No, because you have a net torque. You have this distance and that force, this distance and that force. Each one is going to make it rotate the same direction. So those torques add up. So while the net force on your electric motor is 0, the net torque is not 0, and that's the key. All right, have a great long weekend.